this video, we will discuss the structure of hemoglobin and the binding of oxygen to hemoglobin. Hemoglobin is the oxygen transport molecule of the body. It has an unique ability in loading oxygen in oxygen-rich environments such as lung, while unloading oxygen to the oxygen-extracting tissues. Hemoglobin is near spherical globular protein. It has four subunits, two alpha and two beta subunits. A subunit consists of polypeptide chain and a heme group. Polypeptide chains are built up with amino acids. Interactions between amino acids determine the shape of the polypeptide chain. There are coiled alpha helices comprising 75% of amino acids, and beta-pleated sheets collectively gives the globular shape of the protein. Alpha-globulin has 142 amino acids, whereas beta-globulin has 146 amino acids. There are 8 helical sections in one subunit. Between these helices, there are connecting regions which connect or slide over the other subunits. Subunits arrange in two dimeric halves. Each half move as one rigid body over the other subunit upon binding of oxygen. In this three-dimensional structure of hemoglobin, you can see different subunits in different colors and two subunits in its details. Now we can see clearly in this subunit of hemoglobin the polypeptide chain in silver and gold, and a non-protein component which is the heme group of the subunit in black. Polypeptide chain is in two different forms. The helical structure is alpha helix and non-helical structure is a beta-pleated sheet of amino acids. In the middle of the helical structure, you can see the heme group in black. Four pyrrole groups cyclically bond to form the four-firing ring. In the middle of the four-firing ring, there will be a ferrous atom. The ferrous atom of the heme group bond to imidazole group of the histidine residue, which is in gold color, through a cooperative covalent bond. Oxygen molecule in blue bound to ferrous atom via cooperative covalent bond. On the other side, you can see another subunit which is deoxygenated. And if you see carefully, the gap between histidine residue and the four-firing ring is much narrow in oxygenated subunit. Heme is non-protein prosthetic group. Four pyrrole groups cyclically linked each other by methane bridges, forming four-firing ring. At the center of the four-firing ring, ferrous is held in an unique position. Ferrous ion has 6 binding positions. Ion coordinate with 4 nitrogen atoms of 4 pyrrole groups and covalently bond to nitrogen atoms of imidazole ring of histidine. Except ferrous atom, rest of the atoms of the heme are in one plane. Electron clouds of the imidazole ring of the histidine and electron clouds of the nitrogen atoms of pyrrole groups repel each other. Therefore, iron atom is in a dome-shaped arrangement. Sixth position of iron atom reversibly bind to oxygen by coordinated covalent bond. Upon binding of oxygen with new electron cloud repulsion, ferrous atom drags closer to the heme group plane. Same time, it drags histidine residue which shift other amino acids as well. With that, structure of the interfaces between four subunits change. When oxygen bind with one subunit, two dimeric halves moves 15 degrees one over the other. This result relax or R state of the hemoglobin, where the subsequent binding of oxygen to the other subunits will be relatively easy. Therefore, affinity of hemoglobin to oxygen increases. T state is unbound state where affinity is low. It could be sequential conformational changes with allosteric modulation or concerted reaction where R and T state flip over the other rapidly. This increased affinity of hemoglobin to oxygen upon binding of oxygen is known as cooperative binding. R state of hemoglobin favors oxygenation, where T state resists oxygenation, or in other words, T state favors release of oxygen. Allosteric modulators, which favors T state of hemoglobin, reduce its affinity to oxygen and favors release of oxygen. There are few allosteric modulators which favors T state of hemoglobin or stabilize T state of hemoglobin, thereby reducing the affinity of hemoglobin to oxygen. H plus or acidity of the environment protonate histidine 146 and stabilize T form of hemoglobin. Therefore, it reduces the affinity to oxygen. Acid state favors release of oxygen from hemoglobin. This is the Bohr effect. Carbon dioxide binds with hemoglobin and forms carb-aminohemoglobin, stabilize T form and reduce hemoglobin's affinity to oxygen. Of all, most important allosteric effector for hemoglobin oxygen binding is 2,3-bisphosphoglycerate. It binds to central cavity of beta chains of deoxyhemoglobin. Its stabilized T form reduces affinity of hemoglobin to oxygen. Absence of one histidine residue replaced by serine in fetal hemoglobin reduces binding of 2,3-BPG to fetal hemoglobin. Therefore, fetal hemoglobin has high affinity to oxygen.